So welcome, ladies and gentlemen, to the session of the Nečas Continuum Mechanics. Our speaker today is Dr. Marco Bresciani from the Johannes Kepler University in Linz. So Marco for his PhD in 2022 from the Technical University of Vienna, and then he moved to Erlangen to the group of Manuel Friedrich, and with the group he moved to Linz. So Marco has been working in the area of applied calculus of variations, in particular to quantum mechanics of solids, and he also received a couple of recognitions. So he got a Humboldt Fellowship from the Humboldt Foundation, and besides that, as far as I know, I mean, the second recognition what he got is the Junior Ising Prize, so the Junior Prize of the International Society for interactions between mechanics and mathematics. And today he will tell us something about the growth of cavities and cracks.
Yes, thank you very much, Martin. I usually take advantage of the standing invitation that I have to try what Martin says. I really hear since a couple of days. We really had very interesting conversations about math at Zukia, and I was looking forward for the upcoming week when I'm going to talk also with many people here at Carlin. So what I'm going to talk about is about the problem of quasistatic growth of the cavity and cracks restricted to the plane nonlinear elasticity. And this joint work with Manuel Friedrich, with my mentor at JPU. So the outline of the talk is going to be very simple. So we start with some motivation of how we want to model cavitation and fracture at the same time. After that, I'm going to introduce the model from which our analysis is focused on, which is due to Enao Mora Corral. After that, at step number 3, I'm going to introduce what is our proposed model for the quasistatic growth and our main result, and some proof, some points of the proof will be discussed in section number 4, and then I'll try to take the summary and some possible outlook for future research. Okay, here we're interested in the failure phenomena for soft nonlinear elastic solids and in the quasi-static approximation, so in a sort of slow loading regime. And in this slide, I want just to fix the terminology, so which is the one of cavitation and fracture. So the term of cavitation is borrowed from the theory of fluids because of this fluid counterpart. It refers to the abrupt formation of voids, which mathematically translates in point singularities of solid deformations. Instead, what differentiates it from fracture is that the fracture is more related to jump discontinuities of deformation along hypersurfaces. And here I have this, I propose you this picture taken by the work of Bresciani and collaborators, and which they study, they have some very nice images about fracturing active metals. So this titanium aluminum alloy, so ductile metal indeed. And the first picture is in the scale of millimeters, while the second one is the zoom of this red section, the level of micrometers. So what you can see here, you see that in the second scale, in finer scale, you have this formation of voids that align along this hypersurface, and this basically motivates or gives the idea of a possible fracture initiation by nucleation, growth, and coalescence of voids. So that's what we would like to describe mathematically, even though our results are limited to a very special situation. So we want to have a theory which encompasses both phenomena of cavitation and fracture. And mathematically, these two phenomena are treated in very different frameworks. So concerning cavitation, usually the analysis is set in the framework of solid spaces with the, let's say, the seminal contribution of Milner and Spector that originated to many contributions coming. So this was the first work where the points, there was a free discontinuity problem, so the cavitation points are not prescribed, but are rather an unknown of the problem. There are many other works that originated from it. So some works with prescribed singularities and the work of Enam Moracorral specialized to the setting of cavitation. And I also wanted to mention this very nice, very recent preprint by Anna and Stendhal here that are treating the same problem, so the static case. In the quasi-static case, instead, as far as this pre-discontinuity setting is concerned, I am only aware of this work by Moracorral, where it treats the quasi-static growth of cavities. The literature on fracture is huge, so please forgive me here if I just put a limited list because these are just the works that are more related to what we are doing. Here, the works that I'm mentioning from the early beginnings of Ambrosio to more recent contributions of the polyconvex stored energy concern nonlinear elasticity, so the existence of minimizers, with a subsequent contribution of Giacomini and Consiglione concerning the problem of invertibility of this deformation. And for the quasi-static case, instead of fracture, we have another seminal paper by Dalmas and Lazzaroni, where also included the extent of invertibility in quasi-static obluding setting, and also some specific works on the pure Neumann problem as we are addressing here. And for a variational framework that is able to encompass both phenomena, we just have this model by Enam Moracorral that we are going to describe in quite some detail. And here also mentioned some other contributions, some study based on the phase field approaches to the description of the same energy. So here I'm going to spend a few words to describe indeed the model of Enam Moracorral. So we are allowing for both cavitation and fracture, and deformations of a reference configuration omega and Rn are modeled as special functions of random variation. Here the exponent p is slightly bigger than n-1, where n is the space dimension, and is related to the integrability of Jacobian cofactor. We have the Jacobian determinant has to be positive almost everywhere integrable. We also enforce almost everywhere injectivity, plus boundary condition, plus something like physical components. And the energy that so the model ultimately rests on the minimization of the following energy. Why is the deformation? We are minimizing an elastic energy, which features the stored energy density W, plus some surface energy S, and the also and minus one dimensional measure of the jump set. So, loosely speaking, the surface energy is nothing but the energy created by the deformation through the processes of both fracture and cavitation. So we can think about it as the area of the boundary of the image minus the area of the image, the boundary. So these are the kind of things that are more complicated to write as formula rather than with a picture. So we'll go back later. But this surface energy is going to play a fundamental role in our analysis, so I would like to spend a few words about it. So the expression is this one. So it's written as a supremum of test function on the product of the domain and the codomain. The expression is not really important, but the only point that I want to convey that this surface energy is just giving the area of the new surface created by the deformation. So this expression is quite involved, but finds a complete natural justification in the framework of Cartesian currents. For those of you, if you are familiar, that the surface energy is nothing but is related, let's say, to the mass of the boundary of the current associated to the graph of y. Actually, here is the vertical part, if you may. So the boundedness, this energy was introduced in connection to the problem of the weak continuity of Jacobian. And indeed, what Moracorral and Enau prove is that whenever I have some deformations, let's say, that converge almost everywhere, the cofactor will stay. And the surface energy corresponding to this deformation is uniformly bounded, then you have the weak continuity of the system. Also, what they did, they provided a rigorous definition of a created surface, which is telling you that basically the surface energy Y is nothing but the visible surface created by Y. So really, when you have a crack or a failure phenomena, plus twice the invisible surface. And the invisible surface is originated when you fracture two pieces of material and then you put them in contact again so that it gets invisible for the perimeter. Let me just point out that this point of view, even though it provides a rigorous definition of created surfaces, is not able to distinguish between cracks and cavities. And there are also some further developments concerning the regularity of inverse deformation under the assumption of finite. So as I promised, here we have some pictures. We have a deformation Y of a rectangle. This deformation has some similarity, so it opens some cavities at these points, and it opens this structure here in correspondence of this line. And if I compute the energy, this is giving nothing but the perimeter of the new surface created by Y through the process of cavitation and fracture. So that's the only important message for us. Now, I would like to specialize this theory in the field of solid deformation. So in the modeling fracture. So we are working in this setting with deformation that are W1P with P again strictly greater than N. So I take a point A in omega and I take a radius. I know that for almost every radii, the restriction of my deformation on the sphere centered in A with radius R is continuous. This comes from Murray embedding because of this condition on the exponent. And this continuity assumption is really crucial because it allows us to employ a very powerful tool, which is the topological degree. The topological degree is doing nothing but counting the number of pre-images with sign. So for any such radii, I can define the topological image of the ball of radius R at the set of points where the degree is non-zero. And now by taking smaller and smaller ball, taking the intersection of these sets, I get what is called the topological image of the point. And cavitation points are going to be just those points for which this object here, the topological image of the point, has positive. So again, this is much clearer with the picture. So this is the same picture as before, and we have this point A. What do? We take, as I said, a ball centered in A. I take the image of the sphere, let's say, and it's going to be this blue curve. And the topological image is nothing but all the method is enclosed by this surface. When I go on, I take smaller and smaller radii. At the end, I'm going to take the intersection of all of this, and what I end up is exactly the cavity. So the topological image of any regular point is going to be a set of measures 0, and then the cavities is going to give me exactly the cavities. So the definition is a bit technical, but believe me, this does the right thing that you want. Okay. A very crucial role is played by this condition imp introduced by Müller and Spector for maps that are in our regime, let's say. I don't want to give the definition because it's a bit technical for those who are not familiar with this business. Let me just say that any deformation violating imp is extremely pathological. So it's something that we don't want to include in our class on visible deformation. And also, as the name suggests, is related to invertibility, namely it implies almost linear injectivity. So Enanwar Corral in 2011, they specialized their analysis in the setting of Sobolev maps, and what they obtained is that whenever condition imp is satisfied and the surface energy is finite, then the set of cavitation points is at most countable. They recover the classical formula for the distributional determinant. So it is telling you that the distributional determinant is nothing but the absolutely continuous part is just given by the pointwise determinant, and then you have a singular component which is given by a sum of Dirac deltas concentrated at the cavitation point. And their module, the intensity, let's say, is given by the volume of the cavity. And the surface energy corresponds to exactly what you expect. That is the perimeter of the cavities. So here, the further development, which is also related to our work, is the study by Carlos, who studied the aforementioned variational model in the case of solely cavitation in the setting of quasi-static evolution, because all the ingredients are there in order to implement the analysis. Okay, now I told you about what all the others did. So now it's my turn to tell you what I did. So our intention was to cook up a model who was to allow us to extend the analysis of enamel molecular from the purely static setting to a quasi-static one. So there, the main point for the quasi-static evolution of failure phenomena is being able to enforce the constraint of irreversibility. What does it mean? If I create a cavity or if I fracture at one point, this the matter cannot heal. So this basically enforces the fact that these failure phenomena lead to a dissipation of energy. So what is the problem? The model that I showed you before is set in the framework of special functional boundary variation, but we saw also that to be able to define cavities, we need topological degree, but there is no degree for maps in SPV because these are essentially deeply discontinuous. So our idea to solve the issue, to overcome this issue, let's say, is not really an original idea in the sense that it's just to bring back a tool from the early beginnings of quasi-static fracture growth, starting from the previous works by Dalmas and two others. So the idea is to consider a strong formulation for cracks. So cracks are given by compact subsets in omega, and the deformation is going to be Sobolev map just defined on the crack domain. And this is very nice. However, because of some technicalities that I'm going to mention later, this idea works just in dimension 2. So we're restricted to the plane, and there's some topological restriction on the set of omega. But let me stress that we are in dimension 2, but our problem is fully vectorial, and we are dealing with nonlinearities, and also with an energy that might blow up in the case of extreme compressions. So let me describe briefly our variational model. As I said, I work in dimension 2, and we have some constraint given by an integral m, an integer f. We take any exponent p greater than 1, which is n minus 1 again, and we have some confinement given by its positive constant n. Our domain is a bounded Lipschitz domain R2, so which is the reference configuration, and our energy depends on 3 variables. The first variable is a set of flow points, which are denoted by A. It's just a set of finite points in the closure of omega. The second variable is the crack, and this just given by a compact set K with finite length. And the restriction that we need to impose is that the connectivity of this compact set is a priori bounded. So every admissible crack has at most m connected components. Now, for any configuration of flow points and cracks, the class of admissible deformation is denoted by YAK. Is given by Sobolev maps defined on the crack domain omega minus k, such that they are a priori confined in a biggest ball. This restriction is not really necessary, but it's not too bad because we are nevertheless working in large strain. The Jacobian has to be integrable and positive almost everywhere. They need to satisfy condition in the crack domain, and the set of cavitation point needs to be contained in A. Overall, our class of admissible states is given by a triplet: flow points, crack, and deformation defined on the complement of the crack. Okay. Here, as we do in the paper, for simplicity, I'm focusing just on the pure Neumann problem. So we don't have boundary condition, we just have applied loads. And we're going to consider the following energy. we have fixed time horizon t, and we have some force with values in L1, so since the problem is a priori confined in a big box. And the energy at time t for a set flow point, a crack, and a deformation reads as follows. First, we have the elastic contribution. Then we have the sum of the perimeter of the cavities. Then we have the cardinality of the set A of flow points, plus the length of the crack, H1 of K, minus the force at time t acting against the deformation. So this energy should be understood in the following way. So these terms related to the cardinality of A and the length of K are the only two terms enforcing the dissipation. So if I open a cavity at some point, this energy is lost, and I have to keep track of the fact that this point is broken somehow. The same for the crack. So if I create a crack, the energy used to create this crack is gone, and I cannot recover it. All the other terms related to the elastic deformation, the stretching of this cavity, and the force acting on the body, this can be reversed instead. They are all reversible. And now here I'm listing the assumption on W. They are all standard. So the first one is that W is a C1 on the set of positive matrices, and is equal to plus infinity if the determinant is smaller or equal than 0. So this excludes the reverse of orientation. Then I have some P growth in the deformation gradient plus some volumetric factor, which explodes as the argument goes to 0. So infinite compression leads to infinite energy. And this super linear growth at infinity is volumetric term. So this is also very standard. We require W to be polyconvex. And for the quasi-static analysis, we also need the stress control, which is basically telling you that the stress is controlled by the energy. This looks a bit like the Kirchhoff stress. It's not exactly that guy, but the two can be controlled equivalently under frame indifference assumption. And basically it's telling you that the stress at one point up to multiplicative and additive constant is controlled by the energy. And now I'm ready to state our main result. So we are considering irreversible quasi-static evolution. So these are curves that depend on time. They give you a set of flow points, a crack set, compact, and a deformation. And these are called the reversible quasi-static evolution whenever these conditions are satisfied. First, they satisfy a given initial condition. Second is the irreversibility. Basically, the set functions A and K have to be increasing in time, or better, not decreasing. And the third one is the unilateral global stability. So it means that the energy at time t of my candidate solution is more or equal than the energy at the same time of any other competitor, which opens larger, which open more flow points and as possible a larger crack set. So minimality is not with respect to every competitor, but just with those that experience more failure, let's say. The last condition is the power balance. So the function given by the energy along the solution is absolutely continuous, and they have this energy balance. So the energy at time t minus the initial energy is nothing but given the integral of the power, which is just given in this setting by the work of applied forces. This again is because we don't have, we just focusing on the pure non problem. And our main result is the existence of such irreversible quasi-static evolution. And the theory of this kind of evolution is quite, I mean, we formulated this notion of solution, but the proof strategy, as we see, is pretty standard. And solutions in general are neither expected to be regular, neither unique. They are not regular because they can experience jump because of the formulation, and they are not unique because we are working in the large strain setting. the framework we're adopting, I mean, this model falls within the framework of rate-independent system, which, as I was saying, is really well established nowadays. And the general strategy of the proof is very standard and follows the classical time discretization scheme. So what we do, we discretize our time interval, and for each time step, we solve an incremental minimization problem. We take the piecewise constant interpolations, we apply some a priori estimate, we apply some compactness, and we find some candidate time continuous solution. Then what we do, we need to prove that this solution satisfies the global unilateral stability and the power balance. And again, as I said, some of the steps, for example, the a priori estimate are pretty standard. So here I would like to talk a little bit about the first and the third step, which are the ones that are more tailored to our specific problem that we are working with. So let's talk about the incremental minimization problem. What I need to solve is the following. So for a given time, a given set of flow points, and a given crack, I need to find a minimizer, a k y at time t, among all admissible states that such that the set of flow points contain a0 and the crack contains k0. So it's a minimization problem. I want to prove existence, so I apply the direct method of the calculus of relation. So on the set of flow points and cracks, I consider the absolute distance. So these are compact sets. We are in R2, and so this works. That's the point where we forces us to restrict to the plane case, and with this topological restriction on the set of admissible cracks. Yeah. Okay, and this is related to the applicability of the so-called roll-up theorem, which is basically giving me the lower semi-continuity of this guy here. So we know that this lower semi-continuity holds just in the plane and just if the number of connected components cannot increase to infinity. This is for the first two variables. For the third variable, instead, is the sober deformation on the crack domain, and we consider the weak topology. So overall, here I'm writing the convergence just on omega because K is the set of measure 0. So the weak convergence doesn't detect this. And the key observation here is that if I have a sequence of deformation that yn on the domain cracked by kn, and this satisfying IMB, under the natural notion of convergence, the limiting deformation is going to satisfy IMB again. This is related to a well-known localization property of the absolute distance, which is telling you that if Kn is convergent to K, and if U is well contained in the complement of K, then U is well contained in the complement of Kn for n sufficient to large. So this comes quite for free once you observe this. The formulation of condition IM of crack domain seems pretty new, but for those of you who are familiar with this business, they realize that once you have this trick, this comes quite for free. And the last point, which is very important here, connected to the weak continuity of Jacobian, is to recall the observation that we saw before, that our energy P, which was nothing but the sum of the perimeter of the cavities, coincides exactly to the surface energy, the one related to the created surface at the deformation. And this was for the first point, so the existence. Then we apply our strategy. And the R point now becomes to prove the global stability, global unilateral stability of the limiting, so the candidate solution. So here, the problem reduces to prove the following, which we call the transfer of cavities and cracks. This is a tailored version to our problem, or a very famous theorem, which is the transfer of crack in the setting of quasi-static crack growth. So basically, let me just write one thing. So what we need to prove, we have our stability at level n, let's say, which is telling us that E, An, An, Yn is more than or equal than X. E, An tilde, An tilde, Yn tilde. For every admissible state, and okay, such that satisfies the two conditions. So now I want to prove the same with the candidate solution A and K. So what do? I take any competitor, A tilde, A tilde, Y tilde, that satisfies the right conditions. Sorry. And I have to construct a sequence which approximates my competitor, but I cannot test it here. So what do we say? Suppose that we have our set of our set of flow points that converge to a limiting object, our set of crack that converges to a limiting object. Then we take a competitor for the limiting set with a deformation y tilde. Let's assume without loss of generality that he has finite energy, a finite elastic energy. Then we build a sequence of competitors which are admissible for the problem level n, and this has to satisfy the following properties. So they have to fulfill the constraint. The set of cracks need to converge. Sorry, the set of flow points needs to converge. The set of cracks needs to satisfy the unilateral condition. The cracks converge, and also this energy converged. And we also need to construct a sequence of deformations which converge in measure on the wall domain, and such that the energy converge. And we're able to do this by additionally enforcing the fact that the surface energy stays the same. The construction is explicit, is quite technical, and in particular, while doing all of this, we have to be sure that the in condition is satisfied. So we see that we have many constraints that we have to put together. I'll try to give a rough idea of the construction with some pictures, so because I know it's very technical, but this is the core of the paper, so I think it's I think I really should say something about it. So we have our competitor A tilde, which is the set of flow points plus some other points. And we consider the sequence A tilde n obtained by adding a n this set of extra point a at. So the construction of flow points is easy. Now for the cracks, instead we apply a lemma, which is in Dalmaso to other, which is giving us a sequence of cracks up to some minor modification that I won't want to mention, that satisfies all the constraints and converges to the right value. Now for the construction of the formation, what we want to do? We have our general competitor y tilde, and we have to consider to construct y tilde n. And we are going to do so by a composition with a diffeomorphism of omega. So it is a diffeomorphism which is defined differently, close to cracks and close to flow points. And the fact that this guy is a diffeomorphism is important indeed for fulfilling the in condition. So what do? We have some points here, let's say a n that are converging to a, and we have some points of the limiting crack here. K and tilde is converging to k tilde. Okay. Let me here simplifying a little bit, because I can have also coalescence, which means that copies of multiple cavitation points that converge to the unique limiting cavitation point, but let's avoid this at least for the sake of simplicity. So what do I do after some covering arguments? I cover my cracks with some cubes, and I consider a small ball centered at the point of the sequence. Now I'm going to give you a few indications about how the construction works near the cavities and near the cracks. So the construction near the cavities follows pretty closely this technique of cutoff translation by Carlos. So what do? I take a function, a smooth cutoff function, which is 1 close to 0 and is equal to 0 close to plus infinity, and I define my diffeomorphism as the identity plus this term here. So if you draw a picture, that's pretty easy. I'm in a ball center at the point an with radius epsilon. So this map, what it's doing is fixing the outer circle, and inside the ball of radius epsilon over 2 is just shifting it. So the point an goes to the point A. And everything is glued together in such a way that the overlap map is a diffeomorphism. In particular, both the function and their derivative are the function is equal to the identity on the exterior boundary, and the derivative is equal to 0. So the function arrives flat. The construction instead of deformation near the cracks is much more involved. So here we have to combine various techniques that were around and to tailor it for our specific problem. So our construction is inspired by the paper by Armaso and Lazzaroni when they had some stretching argument to construct deformation near the cracks. The problem is that here they have enough fine stretching, which here we cannot work, because what we hope for is to construct an overall phi n, which is a diffeomorphism. So for not having issue with condition in. So here we instead we cooked up some let's say nonlinear stretching argument of fourth order, and this construction takes advantage of some local separation property of cracks by Giacomini, Lopez, and Pagnies. So here is the reference where we start. We have the set K tilde, which is the red crack that you see on the background, and the set Kn, which is converging to it. So what this property is saying you that both cracks are going to be contained in a stripe at the center of a cube of order epsilon. So when I can do this, then I consider phi as the map that is basically shifting the orange part up and the blue part down. In this way, when I consider the composition, I'm going to look at the point of the deformation that are just here and here, so far from the cracks. Overall, what do I end up obtain is that I'm sure that my deformation is still injective and has the desired regularity, so he has no crack, is still solid deformation. And that's the expression. So it's just a translation in the vertical component with this function G, which is just some fourth order polynomial with the right weights. And now we have constructed this deformation. We just have to be sure that the energy converges. Everything is fine apart from the elastic energy. And there we exploit this condition of the stress controlled by the energy. So why so? Because it was already observed by Ball that this property here is giving you some multiplicative control, multiplicative estimate on the elastic energy. So the elastic energy corresponding to F times G, whenever G, oh, sorry, forgot to say, G has to stay gamma close to the identity, is controlled by the energy of F. So overall, if the gradient of phi is sufficiently close to the identity, I know that the energy of my constructed solution is controlled by the energy of the function of the starting weight. And it's enough because I know that my yn together with the gradient are converging almost everywhere to y, so I can apply dominated convergence. Okay, that's all I wanted to say. Let me just wrap up. So what did we do? We proposed the first evolutionary model for the quasi-static growth of cavity in cracks. And in particular, this model allows for the coalescence of cavities into cracks. So this, in my humble opinion, is very important if you want to develop a theory which is able to describe crack initiation and growth inside of soft elastomers. And we proved the existence of irreversible quasi-static evolutions because of the technology that we are using. Our analysis, as I already told you, is confined in the plane with some topological restriction on the class of admissible cracks. So here I presented the pure Neumann problem, but of course, would be interesting to consider Dirichlet boundary conditions, or possibly time dependent. Here I believe that this should be doable by employing, for example, the technique by Frankfurt and Mietke. So this multiplicative decomposition of the stress. It's just a change of variable that reduces to a problem with time independent boundary condition. So here I have this capital M. So the whole analysis is confined in the build box, but this is just for simplicity again. Otherwise, I can consider, I don't know you call it, is this homogeneous Sobolev spaces. So functions W1 peel off that the gradient is globally integrable, and you can still playing the same game, let's say. So what would be very interested, considering our motivation coming from elastomers, is to consider incompressible of nearly incompressible materials. And the case of growth and of cavities and cracks at the same time seems extremely hard because this construction of the cracks is quite involved. So doing it with additional constraint of being volume preserving seems pretty complicated. I'm working on it with Giuliano Lazzaroni for the quasistatic growth of just the cavities, and this is already pretty technical. So, but it's quite fun. So I hope we will manage to achieve the same result. And let me mention this paper from Giacomini and Lopez Pamiers when they motivate their analysis starting from the fact that is observed in physics that some materials, mostly biological one, experience also healing. So it would be interesting to include healing phenomena, also healing processes also in these kind of models. And lastly, it would be very nice to be able to leave strong formulation and go to a completely weak one with the hope of getting rid of the constraint of plane analysis whatsoever. I was trying to say borrow some techniques by the work of Stendhal and so on with the weak limits of homomorphism in the class of FBD, but I'm afraid that this is not what I need. But it's something I'm thinking about thinking of since long time, and I hope I'll find some ideas in the future. Okay, that's all I wanted to say. So I thank you very much for your attention.